All right, continuing in chapter 2, let's get to this last section where we're going to do what's called modeling using functions to represent plausible real-world scenarios. And the techniques we've learned in this section will help us answer questions about those scenarios. So the objectives are to build and analyze functions. I mean, that's basically it. Really, we're just going to do several examples. This first video, we'll just do one example, and then the 2 more examples in the next one. Okay. So math has an interesting place in sort of study of real-world scenarios, engineering, physics, and that sort of stuff. It is unreasonably effective, is the term used by some philosophers, to describe things. It's very powerful. We can really predict what will happen in the real world and study it based on representing it with math. Okay, but we need to know what functions represent what things and how to manipulate them. Okay, so we assign sort of symbols to things that are variables, stuff like that. You should be sort of familiar with this general concept of using math to represent simplified real-world scenarios. So, for example, let P be a point on the graph of the curve y equals x squared minus 3. Graph the function, and then what I want to do is express the distance from the point xy to the origin as a function of x. And then ask, what's the distance if x is 0? What's the distance if x is 2? What's the distance if x is root 2? So I suggest pausing and trying to figure this out. And I would actually say maybe start with these first. If x is a particular value, then go to the point xy where y is equal to this, and then ask, what's the distance to the origin? And if you can do it for some specific values of x, then come here and try to ask, gosh, what is a general function that represents the distance to the origin? So pause for a moment, try to complete this, and then we'll come back and do it. Okay, so there was one more part to the problem, sorry. It's using a graphing calculator to calculate some stuff. We'll just get to that at the end. So here is the function x squared minus 3. Now, if I'm at the point P of xy, here's the origin, here is my distance d that I want to compute. So here's just the distance formula from the point xy to the point 0, 0. However, it's x squared, it's the square root of x squared plus y squared. But what's y? Y is x squared minus 3. So instead of the square root of x squared plus y squared, if I replace y with x squared minus 3, we end up with this. Notice this is now an x squared minus 3 inside something being squared. If you expand that all out, just FOIL it, you'll get this. Okay, x to the 4th minus 6x squared plus 9. But now notice I have an x squared and a negative 6x squared. So we can simplify that a little bit. So here is your overall function, your distance from 0, 0 to xy, where y must be x squared minus 3. Okay, so this is now a function of x. If x is 0, all you have to do is plug in x equals 0, and you get 3. If x is 2, just plug in x equals 2, and you get root 5. If x is root 2, just plug in root 2. And we don't need a calculator for this, by the way, okay? Because remember, our function d was the square root of x to the 4th minus 5x squared plus 9. So if x is equal to root 2, then x squared is equal to 2, and x to the 4th is x squared squared, which is going to be 4. 2 squared is 4. Okay, and if you simplify all that down, you just get root 3. And if you graph this function, the square root of x to the 4th minus 5x squared plus, here's what it would look like. Notice it does appear to have a minimum at x equals something like 1.58. I'm just going to flip back to a previous slide that has the graph of the original function here. So what does that minimum represent? So the minimum is what point on the curve that's closest to the origin. And it looks like it's somewhere around right here. And x, yeah, it looks like it's between 1 and 2. The x value is somewhere between 1 and 2, and that seems to maybe be closest, and that matches here. We have an x value of something in between 1 and 2 corresponding to the minimum. Okay, and you could use a graphing calculator or a computer program to find that minimum. If you take calculus, you'll learn how to do it by hand. Okay. Also, d of x is an even function. Remember that this function d, which I'll just copy up here again, this was the square root of x to the fourth minus 5x squared plus 9. If you plug in d of minus x, you'll get out exactly the same thing. So it's an even function. So the graph is going to have this sort of symmetry. So if it has a minimum here, it's also going to have a minimum here at x equals negative 1.58. Yeah, so these are the points on that curve that are closest to the origin. Okay, so we'll end this video here. It was a bit short. The next one will also be a little short, just 2 more examples out of this section.